Fire pump and associated electrical equipment grounding is detailed in National Electrical Code Section 695.4b, referencing Article 250. Section 250.112 mandates that all non-current carrying metal parts of the electrical system accessible to personnel must be bonded to the grounding system. This encompasses the fire pump housing, piping, controls, and other metal components. Section 250.66 stipulates the use of grounding electrodes to establish a low impedance path to earth for fault currents. At least 2 grounding electrodes are required, spaced a minimum of 6 feet apart. Regarding wiring requirements, the feeder size from the main switchboard and generator set circuit breaker to the fire pump controller or automatic transfer switch, or ATS, can be either number 1 copper, 3-wire, or number 1 copper, 4-wire. If a 4-wire feeder is used, the neutral conductor must terminate at the main disconnect switch and not at the fire pump controller or ATS. The feeder from the generator set circuit breaker to the fire pump controller or ATS must be 4-wire. A bonding jumper must be installed between the neutral conductor and the grounding conductor at the main disconnect switch. A grounding conductor must be installed between the grounding electrode and the grounding terminal on the fire pump controller or ATS. An equipment bonding conductor must be installed between the fire pump housing and the grounding terminal on the fire pump controller or ATS. To summarize, all non-current carrying metal parts of the fire pump and associated electrical equipment must be bonded to the grounding system. The feeder size can be either number 1 copper, 3-wire, or number 1 copper, 4-wire. If a 4-wire feeder is used, the neutral conductor must be terminated at the main disconnect switch. The feeder from the generator set circuit breaker to the fire pump controller or ATS must be 4-wire. A bonding jumper, grounding conductor, equipment bonding conductor must be installed in accordance with National Electrical Code requirements. Consider the implications of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current circuit, encompassing resistance, inductive reactance, and capacitive reactance. A low impedance ground path is crucial for quickly clearing ground faults. This is because a lower impedance allows for a high fault current, which in turn facilitates the rapid tripping of overcurrent protection devices like circuit breakers. A high impedance ground can limit fault current, potentially delaying or preventing the activation of these protective devices, increasing the risk of equipment damage or electrical shock. The grounding electrode system is vital for maintaining a low impedance ground. It typically consists of multiple grounding electrodes, such as ground rods, ground plates, or buried ground conductors, all bonded together to form a comprehensive grounding network. The National Electrical Code mandates specific requirements for the type, size, and installation of grounding electrodes to ensure adequate performance. The effectiveness of the grounding electrode system is influenced by soil resistivity, which varies dependent on factors like moisture content, temperature, and soil composition. High soil resistivity increases the impedance of the ground path, potentially compromising the effectiveness of the grounding system. Regular testing of the grounding electrode system is recommended to verify its impedance and ensure compliance with applicable standards. Bonding jumpers play a significant role in maintaining a lower impedance path between different metal parts of the electrical system. They are used to connect non-current carrying metal components such as equipment enclosures, conduits, and raceways to the grounding system. By providing a direct, low impedance path for fault currents, bonding jumpers help to minimize voltage differences and prevent electrical shock hazards. The National Electrical Code specifies the required size and installation methods for bonding jumpers, depending on the size of the circuit conductors and the type of equipment being bonded. Proper installation of bonding jumpers is essential for ensuring the effectiveness of the grounding system. The equipment grounding conductor, often referred to as the EGC, is another critical component of the grounding system. It provides a low impedance path for fault currents to return to the source, facilitating the rapid tripping of overcurrent protection devices. The equipment grounding conductor is typically run alongside the circuit conductors and connected to the grounding terminals of equipment and appliances. The National Electrical Code specifies the required size and type of equipment grounding conductor, depending on the size of the circuit conductors and the type of equipment being served. The equipment grounding conductor can be either wire, a metal raceway, or a combination of both, provided it meets the impedance requirements of the code. Proper sizing and installation of the equipment grounding conductor are essential for ensuring the safety and reliability of the electrical system. Regarding the fire pump controller and automatic transfer switch, or ATS, the controller is the central control unit for the fire pump system. It monitors various parameters such as water pressure, flow rate, and motor current, and automatically starts and stops the fire pump as needed to maintain adequate water supply for firefighting operations. The fire pump controller typically includes a variety of control and monitoring features such as alarm indicators, status displays, and communication interfaces. The automatic transfer switch is used to automatically switch the power supply to the fire pump from the normal power source to an alternate power source, such as the generator, in the event of a power outage. This ensures that the fire pump remains operational even when the normal power supply is interrupted. The automatic transfer switch is designed to quickly and reliably switch between power sources, minimizing downtime and maintaining continuous fire protection. The integration of the fire pump controller and the automatic transfer switch is essential for ensuring the reliable and automatic operation of the fire pump system. Let's consider the neutral conductor in a four-wire system. The neutral conductor serves as the return path for unbalanced currents in a three-phase, four-wire system. It is typically grounded at the service entrance to provide a reference point for voltage and to facilitate the operation of overcurrent protection devices. In a fire pump system, the neutral conductor must be properly sized and installed to handle the anticipated unbalanced currents. As previously mentioned, the National Electrical Code requires that the neutral conductor be terminated at the main disconnect switch and not at the fire pump controller or ATS. This is to prevent circulating currents and to ensure proper operation of the grounding system. It's also important to consider the generator set feeder requirement. The generator set feeder provides power to the fire pump system from an alternate power source, such as a generator. The National Electrical Code requires that the generator set feeder be sized to carry the full load current of the fire pump motor, plus any additional loads that may be connected to the generator. The generator set feeder must also be protected by overcurrent protection devices such as circuit breakers or fuses to prevent damage from overload or short circuit conditions. As previously mentioned, the feeder from the generator set circuit breaker to the fire pump controller or ATS must be four-wire. This is to provide a neutral conductor for unbalanced currents and to ensure proper operation of the grounding system. The grounding electrode system should be tested periodically to verify its effectiveness. Ground resistance testing is a common method used to measure the resistance of the grounding electrode system to earth. The test involves injecting a known current into the grounding electrode and measuring the resulting voltage drop. The resistance is then calculated using Ohm's law. The measured resistance should be below a specified value, typically 25 ohms or less, to ensure adequate grounding performance. If the measured resistance is too high, additional grounding electrodes may be required to improve the grounding system. Visual inspection should also be conducted regularly to check for any signs of damage or corrosion to the grounding electrodes and connections. Damaged or corroded components should be repaired or replaced promptly to maintain the integrity of the grounding system. The grounding system should also be tested whenever any modifications or additions are made to the electrical system. This is to ensure that the grounding system continues to meet the requirements of the National Electrical Code and to provide adequate protection against electrical shock and equipment damage. When dealing with a 75 horsepower, 480 volts, three-phase fire pump, several calculations and considerations are necessary to ensure proper grounding and wiring. Firstly, calculate the full load current of the fire pump motor. Use the National Electrical Code Table 430.250 to determine the full load current for a 480 volts, three-phase motor. For a 75 horsepower motor, the full load current is approximately 96 amps. Secondly, determine the minimum size of the feeder conductors. The feeder conductors must be sized to carry at least 125% of the full load current of the motor, as required by the National Electrical Code Section 430.22. In this case, 1.25 times 96 amps equals 120 amps. Therefore, the feeder conductors must be sized to carry at least 120 amps. According to the National Electrical Code Table 310.16, number 1 copper conductors with a 75°C insulation rating are typically suitable for carrying 120 amps. Thirdly, calculate the minimum size of the equipment grounding conductor. The equipment grounding conductor must be sized in accordance with the National Electrical Code Table 250.122, based on the size of the overcurrent protection device. In this case, the overcurrent protection device is a 175 amps magnetic unicircuit breaker. According to the National Electrical Code Table 250.122, a number 6 copper equipment grounding conductor is required for a 175 amps overcurrent protection device. Fourthly, determine the grounding electrode requirements. The National Electrical Code Section 250.50 requires that all grounding electrodes be bonded together to form a grounding electrode system. This typically includes a combination of ground rods, ground plates, or metal water pipes. At least 2 grounding electrodes must be installed, spaced at least 6 feet apart. The grounding electrode conductor must be sized in accordance with the National Electrical Code Table 250.66, based on the size of the service entrance conductors. Fifthly, consider the bonding requirements. The National Electrical Code Section 250.92 requires that all metal parts of the electrical system that are likely to become energized be bonded together to form a low-impedance ground path. This includes metal conduits, metal enclosures, and metal equipment frames. Bonding jumpers must be sized in accordance with the National Electrical Code Table 250.102, based on the size of the circuit conductors. When installing the grounding and bonding conductors, several best practices should be followed to ensure proper performance and safety. Firstly, use listed and labeled grounding and bonding connectors. The connectors should be suitable for the size and type of conductors being used and should be installed in accordance with the manufacturer's instructions. Secondly, ensure that all grounding and bonding connections are clean and tight. Remove any dirt, corrosion, or paint from the surfaces before making the connections. Tighten the connections securely to ensure good electrical contact. Thirdly, protect grounding and bonding conductors from physical damage. Run the conductors in a manner that minimizes the risk of damage from impact, abrasion, or corrosion. Use conduit or other protective measures where necessary. Fourthly, avoid creating ground loops. A ground loop occurs when there are multiple ground paths between 2 points, which can create circulating currents and interference. To avoid ground loops, ensure that there is only one ground path between each piece of equipment and the grounding electrode system. Fifthly, document the grounding and bonding system. Keep a record of the size, type, and location of all grounding and bonding conductors and connections. This will make it easier to inspect and maintain the system in the future. When dealing with the tap ahead of the main in the switchboard through a 600 amps disconnect switch to the fire pump controller or ATS, several additional considerations are necessary. Firstly, ensure that the tap conductors are sized in accordance with the National Electrical Code Section 240.21b. The tap conductors must have an ampacity of at least 1/3 of the rating of the overcurrent protection device protecting the main feeder. In this case, the main feeder is protected by a 600 amps overcurrent protection device, so the tap conductors must have an ampacity of at least 200 amps. Secondly, ensure that the tap conductors are protected from overcurrent at their point of termination. This can be accomplished by installing an overcurrent protection device, such as a circuit breaker or fuse, at the load end of the tap conductors. The overcurrent protection device must be sized to protect the tap conductors in accordance with the National Electrical Code Section 240.4. Thirdly, ensure that the disconnect switch is properly rated for the application. The disconnect switch must have a voltage rating equal to or greater than the system voltage and a current rating equal to or greater than the load current. The disconnect switch must also be horsepower rated if it is used to disconnect a motor load. Fourthly, ensure that the disconnect switch is readily accessible and clearly labeled. The disconnect switch must be located in a readily accessible location and must be clearly labeled to indicate its purpose. This will make it easier to disconnect the power to the fire pump system in an emergency. Fifthly, consider the selective coordination requirements. The National Electrical Code Section 700.27 requires that emergency systems such as fire pump systems be selectively coordinated to ensure that a fault on one part of the system does not cause a complete shutdown of the system. This means that the overcurrent protection devices must be selected and coordinated so that the device closest to the fault will trip first, while the other devices remain closed. Selective coordination can be achieved through the use of fuses, circuit breakers with adjustable trip settings, or other coordination devices. In addition to the National Electrical Code requirements, there may be local codes or regulations that apply to fire pump systems. These local codes or regulations may impose additional requirements for grounding, wiring, bonding, or other aspects of the system. It is important to check with the local authorities to determine what codes or regulations apply to your specific project. Regular maintenance and testing of the fire pump system are essential for ensuring its continued reliability and performance. The National Fire Protection Association, or NFPA 25, provides guidelines for the inspection, testing, and maintenance of water-based fire protection systems, including fire pump systems. The NFPA 25 recommends that fire pump systems be inspected and tested on a regular basis to verify that they are operating properly. The inspections and tests should include the following checks. Firstly, check the water supply. Verify that the water supply is adequate and that the water pressure is within the required range. Secondly, check the pump. Inspect the pump for any signs of damage or wear. Verify that the pump is operating smoothly and that the pump discharge pressure is within the required range. Thirdly, check the motor. Inspect the motor for any signs of damage or wear. Verify that the motor is operating smoothly and that the motor current is within the rated range. Fourthly, check the controller. Inspect the controller for any signs of damage or wear. Verify that the controller is operating properly and that all of the alarm and status indicators are functioning correctly. Fifthly, check the automatic transfer switch. Inspect the automatic transfer switch for any signs of damage or wear. Verify that the automatic transfer switch is operating properly and that it is switching the power supply to the fire pump from the normal power source to the alternate power source in the event of a power outage. Sixthly, check the batteries. Inspect the batteries for any signs of damage or wear. Verify that the batteries are fully charged and that they are providing the correct voltage. Seventhly, check the alarms. Test all of the alarm circuits to verify that they are functioning correctly. Verify that the alarms are audible and visible. Eighthly, check the flow rate. Measure the flow rate of the fire pump to verify that it is within the required range. The flow rate should be measured at various discharge pressures to determine the pump's performance curve. Ninthly, check the system piping. Inspect the system piping for any signs of leaks, corrosion, or damage. Repair or replace any damaged piping as necessary. Tenthly, check the system valves. Inspect the system valves for any signs of leaks, corrosion, or damage. Verify that the valves are operating smoothly and that they are in the correct position. Any deficiencies identified during the inspections and tests should be corrected promptly to ensure the continued reliability and performance of the fire pump system. Proper grounding and wiring are essential for the safe and reliable operation of fire pump systems. By following the requirements of the National Electrical Code, the recommendations of NFPA 25, and the best practices outlined in this discussion, electrical professionals can ensure that fire pump systems are properly grounded, wired, and maintained to provide reliable fire protection for buildings and occupants. Remember to always consult with a qualified electrical engineer or inspector to ensure that your fire pump system complies with all applicable codes and regulations.